This is part B in our introduction to Fourier analysis. A reminder that all of the videos in this series, the playlist for those videos, is featured at the website at digital-university.org. In this video, we just want to spend a few moments discussing odd functions and even functions. The definition for an even function is f of minus x is the same thing as f of x. An example would be the cosine of x. F of minus x, that equals minus f of x, that's an odd function. And the sine is an example of an odd function. In a moment, we'll try to sketch out some other odd functions and even functions and visually try to illustrate some of their salient characteristics. Before we do that, though, let's consider what happens if we multiply together two odd functions. Let's say we have a function f of x, and it's an odd function, and say we have another function f of y, and that's an odd function. We multiply them together. So here we would have that f of minus x times f of minus y. Well, this is equal to, since this is an odd function, this would be minus 1 times f of x, and this is minus 1 times f of y. Minus 1 times minus 1 is plus 1, so this equals fx times fy. And this is the definition of an even function. So two odd functions multiplied together yields an even function. And needless to say, if we have two even functions multiplied together, we get an even function. And it's very simple to show that if you have an odd function times an even function, you get an odd function. Just by going through these few little steps right here. Okay, now let's just take a look. We said that for an even function, f of minus x equals f of x. So for example, suppose we had say this, a function that looked like this. Here we're at minus a, and here we're at plus a. So clearly, f of minus x is the same thing as f of x. That would be an even function. Suppose we had one that was like this. And we stopped here. Then clearly, let's just demarcate this. Here, where f of x gives plus value of y, here f of minus x gives a minus value of y. The magnitude or the absolute value would be the same, but here then, as we go over to minus x, we're going down y units, where here for a certain x, we're going up y units. So here, for an even function, they say that it's symmetric about the y-axis. For an odd function, in a lot of textbooks they'll say that it is symmetric about the origin. For example, here we would go over to the right a units, then go up b units. On this side we go to the left a units, then we go down b units. Or you could imagine taking this and just rotating it about the x-axis, and then again rotate it about, take this, rotate about the y-axis, then again rotate it about the x-axis, and I'll give you this. That's another characteristic of an odd function. Take the upper half here, rotate it about the x-axis, then rotate again about the y-axis, and you get the function down here. Either way, these are just basic characteristics of even functions and odd functions. But let's look at this one. Suppose we have an even function then, and we are integrating it, say from minus a to plus a of f of x dx. Clearly then, this is going to be equal to the integral from 0 to a of f of x dx times 2. And for our odd function, if we're integrating from minus a to plus a of f of x dx, that equals 0. And here the a is clearly the way we've drawn it then would be like the end of the function here. So if this was repeating, then this would be going from minus t to plus t, minus t to plus t, or from 0 to t. Well, for an odd function, this integral is 0. And for an even function, then we could write this integral as 2 times this integral. When I remember our formulas for the Fourier coefficients, we have a sub n equals, say, 2 over t, 0 to t, or we could write it from minus t over 2 to plus t over 2 of a function f of t times the cosine, say, of n omega naught t dt. Well, if this is an odd function, then we multiply it with an even function here, and we do that kind of an integral, it comes out to be 0. So if f of t is an odd function, then there are no cosine terms in the Fourier expansion series, because all the a sub n's, these Fourier expansion coefficients, all of them will be 0. Now, if we're looking at b sub n, here's an odd function times an odd function. That gives us an even function. And then if we want for an integral like this, or like this, we can rewrite like this. And we'll have an example of this in the future videos. So I just want to point out here then that when you're using the Fourier expansion method, if the function is even, for an even function, now you only have cosine terms. Because if this was even, and this is an odd function, then you have an odd function, and when you integrate that, you're going to get 0. So all of these Fourier coefficients are 0, so there's no sine terms. If you have an odd function, then there's only sine terms. If this is odd, that's odd. It comes out an even function. So we get our b sub n expansion coefficients. But for the a sub n's, for our odd function, and now we have a cosine here, that's odd, that's even. Now we're not going to have any a sub n's for our Fourier expansion coefficients. Therefore, there won't be any cosine terms. So when you have an even function, expect to see only cosine terms. When you have an odd function, expect to see only sine terms. And again, just as a brief reminder, this is one of the, as we showed in the previous video, this is one of our standard formulas that we use for the Fourier expansion. And here's a sub n, here's b sub n. So if this is even, and this is even, this would be an even function. We can determine a sub n. But if this is even and this is odd, multiply it together, you get an odd function. That comes out 0. Just like we showed right here. If f of t is an odd function, multiply it by an even function, then this comes out to be 0 now, because this will be an, altogether, this will be an odd function. So now this is 0, no cosine terms. This is an odd function times an odd function, gives an even function. This integral will exist. We'll only have then b sub n terms, and therefore only sine values in our Fourier expansion. And again, we'll have some specific examples to illustrate this, and we'll be commenting later on in those videos. We'll harken back to what we'd covered here in this video. But again, just a brief reminder then that you can expect to see that even functions have only cosine terms and odd functions have only sine terms. And that, again, the whole thing harkens back to that. Multiply two odd functions together, you get an even function. Multiply an odd function or an even function together, you get an odd function. Okay, that's it for this video. Come back and join us for the next video. We're going to use our formulas here to solve a specific problem. And then in video number 5, we're going to use this expression to derive the exponential complex form of Fourier expansion technique. So come back, join us for those videos, and we will start solving some specific problems.